This is my nightmare. Being asked over and over which one should be posted and having no clue. Even though I choose one, I end up getting pushback. But not anymore. Because AI will do that for me. I decide to build an AI that takes the post options and returns the one with the highest engagement. Let's dive right into the project. Since I'm doing this for my friend, sorry, big sister, that's why this project needs to be perfect. I want the dataset to reflect what she would actually post, so the genre can be considered a lifestyle blog. And I choose to scrape data from users with follower counts between 10k to 100k, because that's the range where posts are relatable, yet still get decent engagement. And my engagement metric is likes to follower ratio to normalize the results. After a bit of scraping, my dataset became 2,918 Instagram posts, which means even though it's a regression problem, we also need deep learning to properly handle images. Deep learning is a part of machine learning that uses neural networks with multiple layers to automatically learn features from raw data like images, text, or audio. It has many architectures, but for computer vision, the backbone is CNNs. CNNs are built using convolutional layers, so before moving on, let's quickly understand how these layers work. Here we have our 6 to 6 pixels image and the filter, also called a kernel. Kernel is a small matrix that slides across the image. It can be 3 to 3, 5 to 5, 7 to 7, and so on, but stacking smaller ones is usually more efficient. The kernel starts from the top left corner of the image. In each slide, what happens is that it adjusts the same learnable weights, which in our case come from the 3 to 3 kernel, and 3 RGB channels of each pixel, which makes 27 learnable weights. At the same time, it calculates the dot product between the filter and the local patch of the image. That dot product is placed into a new matrix called the feature map, which will be used by the following layers. And that mechanism is actually what convolution means. Convolution is this operation where the same small set of weights, the kernel, slides across the entire image, taking dot products with every local patch. And after we have the feature map, there's usually a pooling stage that goes through it in small patches, such as 2 to 2, and keeps the part where we have strong signal or higher value. And that's what a convolutional neural network is made of. And this is the result, which totally failed. But actually, it's expected because I only have 3,000 images. To train a deep learning model from scratch, we would normally need hundreds of thousands or even millions of images. Seeing DynoV3 has trained with 1.7 billion image dataset and Clip has trained with 400 image text pairs. To handle this limited data, I could keep scraping until Instagram sends me a cease and desist letter, but there's also another way. Fine-tuning means taking a pre-trained model, which already trained on a large dataset, and adjusting it to perform well on usually smaller or more specific tasks. This way, we can benefit from model's existing knowledge while making it work for our own case. There are several ways to fine-tune a model, and I want to go with the most classical and straightforward approach. Unfreezing some of the later layers while keeping the early ones frozen. And speaking of CNNs, what I'm looking for is a light and fast CNN. Actually, I could use transformers as well since they are newer and more suitable, but I've already started working with CNNs, so I will go with good old EfficientNet. I know it's not that old, but in this field, even a 2-year algorithm is considered nostalgic. Back to EfficientNet, it uses special blocks that contain a different structure of convolution layers, which make the network lighter and faster. Also includes a squeeze and excitation mechanism, a lightweight channel attention model that kind of works like a primitive form of self-attention in transformers, helping the model focus on the most informative features in each image. This design allows it to achieve higher accuracy with fewer parameters and lower computational cost than most conventional CNN. Before fine-tuning it, let's go through the blocks based on this image and see which ones will be frozen. The first few blocks handle the basic stuff. They detect things like edges, colors, textures. And as you can see here, it kind of gets the edges of the image, like the outline of the image. It also understands how fat my cat is by detecting the outlines and identifying the areas where the fur is white and orange. Then we move to the middle blocks. These go deeper and they start recognizing shapes, corners, and object parts. So in our case, we can see that it kind of understood where the mirror, the cat, and eye are in this image. Not sure if it was more understandable before the drawing. Let's move on. And the last layers are where the real meaning kicks in. These layers capture high-level concepts, such as this area is the cat, this is the background. Bright areas correspond to the regions the model finds the most relevant. And these are the layers I will unfreeze so the model can learn the specific patterns in our Instagram dataset without forgetting its general visual knowledge. Also, we kind of dived into CNNs and the vision side of things, but the main goal is actually to predict engagement, meaning the model needs to not only understand what makes an image Instagrammable, but also learns which ones are likely to get high engagement. And this is the part where we need to add regression to our pipeline, which we can do by attaching a regressor head to the model. Normally, EfficientNet ends with a classifier head, a fully connected layer that outputs class logits. But in this setup, that classifier is replaced, so instead of class probabilities, the model outputs embedding vector, a compact representation of the image's high-level visual features. The regressor head then takes this embedding and produces a single continuous value representing the predicted engagement ratio. During training, the loss between the predicted and true engagement values flows backward through both regressor and the unfrozen efficient layers, slightly adjusting the high-level filters so the embeddings become tuned for engagement-related visual semantics instead of generic ImageNet categories. The model has learned the general pattern, but not perfectly. It's a valid partial success. It understands directionally which images perform better, but is still fuzzy in low-value regions. I think this will do my sister's job, so now I can sit back and relax. Well, I was expecting that, so let's get back to the project. We need to add captions to our dataset as well, and whenever we mix images and text in AI, we officially enter to the world of vision language models. VLMs are AI systems that can understand both textual and visual inputs. And in our case, we need a model that will both take the image and its corresponding caption. And that's where I will be using Clip. Clip's main goal is to pull matching image-text embeddings closer together and push apart those that don't match. And if you want a deeper dive in Clip in just a minute, you can check out my shorts on it as well. And for this project, of course, we need to fine-tune Clip as well. And let's understand how we will be doing it. Clip is built from two transformers, one for text and one for vision. Each has 12 layers, and as you go deeper, the understanding becomes more meaningful. In the vision transformer, the early layers focus on low-level features like edges, colors, and small textures. And the middle layers start capturing structure and relationship, such as shapes, objects, and spatial relationships. And the final layers handle abstract reasoning. And on the text side, early layers detect basic language features like characters, punctuation. The middle layer starts understanding the grammar, phrases, and the final layers capture semantic meaning, like the intent behind the sentence. And for our project, we will be unfreezing the last three layers from both transformers for them to understand the relationship between the captions and the image. And within that, our training pipeline becomes something like this. First, Clip takes both the image and its caption as inputs, then creates embeddings for both the image and the text. Then these two embeddings are concatenated into a single multimodal feature vector and fed into the regression head, which predicts the engagement score. During training, the prediction error generates gradients that flow backward through the regression head and into the last three transformer layers of both Clip's visual encoder and text encoder, which are the layers I kept unfrozen. And as a result, this slightly reshapes Clip's embedding space, which means high engagement image caption pairs are pulled closer together, while less engaging ones are pushed apart. So in short, fine-tuning Clip with unfreezing the last three layers helps Clip better understand which image and caption combinations attract attention. Let's see the results together. Fine-tuned Clip pipelines successfully learned a meaningful relationship between Instagram post semantics and engagement, demonstrated a clear positive correlation between predictions and actual values. And this was achieved with only about 3,000 image caption pairs. Compared to the previous models I tried, a from-scratch deep learning model completely failed to capture this relationship, and while EfficientNet showed some promise, Clip clearly delivered the best results. Ultimately, besides the graphs and numbers, the best way to understand its success is to test it directly on real Instagram posts. Here's a quick question for you. Which one do you think got the higher engagement? This is what the model have chosen. And this is the correct one. So, here's another one. So the model's performance is quite well on the actual posts as well. So I am letting my sister know about that. Meanwhile, we can check which features the model is paying attention to.